Now here is the pH scale. So you can see since carbon dioxide is low at the surface, pH is going to be a little higher at the surface. Because again, there's less carbon dioxide, so there's less carbonic acid, it's less acidic. That means a higher pH. But as carbon dioxide increases, you see a decrease in the pH. Again, because more carbon dioxide, more carbonic acid, and a lower pH, more acidic. So they kind of go in opposite directions here. Next thing we're going to talk about is how light behaves in the water, because light is a very important part of the marine environment. So first off, as you've probably even noticed if you've like dove to the bottom of the pool, it's like a little more twilighty down there. It's not quite as bright once you get down into the pool. As you go down, there's less and less light until once you get deep enough, there is no light, right? It's completely dark. And that is because water molecules, as well as anything that's dissolved in the water molecules, both absorb and scatter the light. And we call that process attenuation. That's just a decrease in the intensity of light with depth. So what a light attenuation means is just as you go from the surface deeper and deeper and deeper, you get dimmer and dimmer and dimmer in terms of light. There's less and less and less light. So that's light attenuation. And again, it's because of the absorption and scattering. Now, when we look at how light is absorbed in the ocean, it's not like all wavelengths of light are absorbed the same. So red light is absorbed first. So as you're going down, the color of light that will go away first is red, and the one that'll go away last is blue. And so at a certain depth, all that's left, because of all the light's attenuated, except for blue. And so everything looks blue because the only thing that's there is blue light. And you can see this in photography. So if you're a photographer and you're like decently deep into the water and you forgot your flash, you'll take pictures that look like this, where they're kind of dim, right? Because the light has attenuated, and they look very, very kind of gray blue because all other wavelengths of light have been absorbed and scattered. But if you use a flash, now you can see the true colors of what we're looking at. There's yellow, there's red. This is like a red t-shirt right here. So when you bring a flash, you're adding white light again, and so you can see all the true colors of what you're looking at. Another thing we talked about light in the water is the turbidity. So turbidity is just how clear or murky is a liquid. So if you have like pure water, or like pool water, that's very low turbidity. It's very, very clear. And in very, very clear water, light will penetrate a lot deeper. Whereas if you have high turbidity, think very like cloudy water. Maybe there's a lot of sediment. Maybe there's a lot of phytoplankton. It's making that water murky in color. And when there's higher turbidity, light attenuates faster. So you'll have less light penetration. That means you won't have to go that deep for like it gets dark. All the light has attenuated. Hi, baby. So you can also think like this murky water. This is more like the water we have here in California, where it's fairly high turbidity, it's fairly murky water. Whereas like this low turbidity, this might be what you'd find in like the Caribbean, right? They have that blue, like clear water. And that's necessarily like a bad thing. There are very many like natural processes that'll lead to more or less turbid water. For instance, we have way more phytoplankton here than they do in the Caribbean. So that's one of the reasons our water has much higher turbidity. So, next question for you guys is, so again, imagine like low turbidity water, super crystal clear, high turbidity water, very like murky, almost muddy looking water. How do you think living things might be affected by the turbidity of the water, by how clear the water is?